So today we're going to have a look at two things. So there's two topics on this slide. We're going to have a look at type 1 and type 2 errors, and then we're going to have a look at distribution curves in relation to the standard deviation. And that's inferential stats covered. Okay, so no more maths for a while until we sort of come back to it for revision later. So we're going to start with type 1 and type 2 errors and what they are. And the photographs there are sort of a good illustration of what a type 1 and a type 2 error could be. So a type 1 is known as a false positive error, so it's something that's untrue basically. So it would be as like the picture telling a man that he's pregnant, whereas a type 2 error is the opposite. It's a false negative. So you're sort of denying the truth in other words. So as the picture demonstrates, you've got a woman who is clearly heavily pregnant being told that she's not pregnant. Okay, so think about those images. And that might give you a sort of visual representation of what type 1 and type 2 errors are about. So a type 1 error, okay, a way to learn this, okay, to help you remember is to think type 1 begins with O, and O is linked to optimism. So type 1 is an optimistic error. Okay, so it refers to a situation when we assume that our findings mean something when really they don't. Yeah, so in other words, we're rejecting a null hypothesis that is true. So we're drawing the wrong conclusion. We're saying we have a significant result. We're accepting our alternative hypothesis when really we're incorrect. So in other words, we're assuming the results were due to the IV if it was an experimental design, when in fact they're more likely to be due to chance, in other words. So what we should have done really is keep the null rather than reject it. Okay, so an optimistic error is when we've kept our null hypothesis, but what we should have done is actually reject it. When does it happen? It's all linked to where you set your p-value. So if you set it too leniently, e.g. setting it at the sort of 10% level, so p is equal to or less than 0.10, you're more likely to make a type 1 error because you've got more chance introduced. Okay, so there's more possibility that that your results are going to be due to chance, because 10% isn't as sort of stringent as the sort of 5% probability level. So you're introducing more opportunity to sort of make the wrong decision because you've allowed more for probability. And then type 2 is the opposite error. So a way to remember this is to think of 2 and to think of the phrase better to be safe than sorry, okay, which is sort of kind of indicating that you're being cautious about something. So that means when you get a type 2 error, it's a situation where you're actually accepting the null, okay, when really what you should have done is accept your alternative hypothesis, and what you've done here is rejected it. So in other words, what you're doing is that you're saying the results are due to chance, because you're accepting your null hypothesis, when really, they were in fact true. So what you should have done really is reject it. Therefore, we should have rejected the null hypothesis rather than accepting it. Okay, so it's the opposite of a type 1 situation. So based on our logic previously, when are we more likely to get them? You're more likely to get them when you set your p-value too stringently. Okay, so rather than setting it at p is equal to or less than 0.05, you're setting it at p is equal to or less than 0.01. So you're allowing a 1% error rate for chance rather than 5%. So you're setting it more stringently. Okay, that's Nairin sneezing. So you're more likely to get it when you're being stringent. However, as we've talked about, sometimes you need that stringency. Medical research would set their p-values very stringently. Okay, so sometimes it is necessary to set them quite stringently at 1% or perhaps even 0.001. Okay, so those are type 1 and type 2 errors, so you do need to know about them and when they're likely to occur. Okay, our next topic is just a reminder as well, okay, about a question that you might be asked about when you should use parametric and non-parametric tests. We've talked about this previously. So the 5 that we've just looked at are all non-parametric tests, okay? But you might need to know when we use parametric tests, okay? That might come up on the exam. So just a reminder, we've talked about this before, those are our reasons for when we use parametric tests. And very often we can't use them in psychology, as we've talked about, because we don't meet the criteria. So we don't often have, as it says there, we don't often have an interval level scale, okay? Often we're working with ordinal or nominal data. We also need a normal distribution, which we'll talk about in a second with the slides that follow. So those are the sort of main reasons. We can't assume that we've got a normal distribution, and we can't assume, we're not working with an interval scale. So if we don't meet those 2 criteria, then we have to use the non-parametric tests that we've been looked at, which assume that you haven't got a normal distribution and you can calculate them with more than just interval data. Okay, so just a reminder about when we use parametric and non-parametric tests. Right, final bit, okay, very final bit of stats is looking at distribution curves, and you need to know what a normal distribution curve represents, and you need to know what skewed distributions look like, okay? You're not going to be asked anything too complicated here, but you just need to be familiar with what a distribution curve represents. So that's a normal distribution, that's our normal bell-shaped curve. We've looked at this before. And in a normal distribution, okay, what it's representing here is the standard deviations, which we've calculated and looked at previously. So in a normal distribution, okay, you have this bell-shaped curve, and our mean, our median, and our mode will all fall in the same place. Okay, so they're all the same. They'll all fall at this point here. Okay, so that's your average. The standard deviation will then tell you how spread out it is, either side of the curve. It'll tell you how big those gaps are. And it also tells you on the distribution curve what proportion of people fall within certain standard deviations. So as you can see, these percentages here, 68% of people will fall within 1 standard deviation of the mean. So the majority of people on a test or on in terms of their shoe size or in terms of their intelligence, they'll fall within 68%. 68% of scores will fall within 1 standard deviation of the mean. Okay, so they're sort of the majority of people are around these averages. 95% of people, or just above, okay, fall within 2 standard deviations of the mean. So look at your percentages. 68% of scores are here. The proportion of scores that are here would be sort of 27%. Okay, so we're taking 68 from 95, that would be 27% of the population. And then at the extremes, 3 standard deviations from the mean, that represents 99.73% of the population. Okay, and so these little tails here make up 5% of the population. So we have 5% of the population falling within this sort of 2 to 3 standard deviations of the mean. Okay, So remember, your curve is symmetrical, so you have scores fall in this side and scores fall in that side. So this sort of 68% here, if that's the mean, if that was shoe size, and we're saying that's a female size 6, we know, okay, 68% are within one standard deviation. 33% of people here are going to have a shoe size bigger than a 6, yeah? And 33% of people here are going to have a shoe size of less than a 6. So maybe, depends on the standard deviation, perhaps this represents shoe sizes 6 to 7, and this represents shoe sizes 5 to 6. Okay, similarly at the extremes, yeah, we know that this is 5%, so we have 2.5% here and 2.5% here. So in terms of shoe sizes, these little tail ends might represent, for a woman, yeah, these might be women that have a shoe size of a 9 this side, yeah, or maybe this side, women with really tiny feet, they might be a sort of 2 or a 3 represented here. Okay, so that's what our curve tells us. So when you know what your standard deviation is, which we've calculated, it can tell you what these represent. Okay, so here's an example. Charlotte and Rachel have timed people on a test. They've worked out their mean score is 15. Okay, so that would represent the 15. And they've calculated their standard deviation to be 2 minutes. Okay, so if that's 15 and that one standard deviation represents 2 minutes, we know in this proportion, okay, if that's 15, 34% of people, okay, are going to have a score of between 15 and 17. Okay, that would represent this proportion. And this proportion, 34% of people would have a score of between 15 and 13. Okay, so we know, as it says there, that 68% of the people in her sample are going to have scores of between 13, okay, and 17. So here's a question for you. If one of the participants took only 11 minutes, okay, how many standard deviations are they likely to be from the mean? I'll give you some time to think about it. So if one of the participants took only 11 minutes, how many standard deviations are they away from the mean? So 15, yeah, minus 11 gives us 4 minutes. We know that one standard deviation equals 2 minutes. So therefore they're 2 standard deviations from the mean. Okay, so they took only 11 minutes. So they're going to be here, aren't they? Yeah, so they're taking less time than the average. So they're going to be 2 standard deviations from the mean. Second question, what percentage of the population would be faster than this in the sample? So they are 2 to 3. Yeah, look at the percentages. So if that represents 5% of the population, we're cutting our curve in half. 2.5% of the population would be faster than this. Okay. So that just explains what a normal distribution curve shows in a bit more detail than we've done previously. And then just finally, final topic, okay, is that you do need to know what a skew distribution is. And there's 2 skew distributions there. So what you can see is that we haven't got our nice symmetrical bell-shaped curve. We have a sort of skew either to the left or to the right. And you can see how it affects the averages. Okay, so a positive skew, yeah, we've got, the way to remember this is to look at the tail. So a positive skew means that your long tail shifts to the right. okay, whereas a negative skew shifts to the left. So typical question you get is a multiple choice. They'll give you the curve and they'll ask you to say, you know, what is this? Yeah, and for a mark. Just talking about the averages. Okay, so if you can look at our averages, you can see that they've shifted around. So you might be asked to identify where they are on a curve. So they might ask you, where's the median? So it's easy to figure these out. Yeah, so the rules to remember is the median, okay, is always the midpoint because it's the middle value. Okay, so that one's always in the middle. And then the mean, okay, is the one that shifts around the most because it takes all scores into account. So you can see it follows the tail. Okay, so the median's always the one in the middle. The X with a hat, the mean follows the curve, and then the mode is always the most frequently occurring value, so it's always the top of the curve. Okay, so the mode is always top of the curve, the